This video is about modeling linear functions with an equation. This is part one. So what makes a function linear? Well, this should give you an idea. The easiest answer is that the graph forms a straight line. That's why it's called linear. We can see the word line in the word linear. But what makes a line? Well, this is a little bit harder to explain. But you can see that these points on this graph form a straight line. How do we know they form a straight line? They seem to line up. But maybe they were off by just a little bit and they just appeared to be all lined up. Let's try to find out. Well, we can see if we go from the first point to the second point, so as x goes up by 1, y goes up by 150. The same thing happens here. X goes up 1, y goes up 150, and that keeps happening over and over again. That's how we know that the points line up perfectly. If they didn't, if we went over 1 and then up, let's say 450, our next point would be way up there. And obviously that would not make a line. It would not be linear. So how does this help us? Well, this can help us create the equation if we look at the table. So we already know from just looking at the graph that when x, the months, is 1, y, the number of visitors, was 150. We had 2, 300, 3, 450. We're just reading these from the points on the graph. 4, 600. So what about 100? What if we went by 100 months? How many visitors would there be after 100 months? How could we figure that out? Well, again, we can look at the pattern that's going on both in the graph and in the table. Right? When we go from 1 to 2, we're going up 1 in the x direction. We're going up 150. We already knew this pattern from looking at the graph, but here it is in the table. We can use that in the work. So we start off with 150, and then we do 150 plus 150 to get us our 300. Then for the next one, we do 150 plus 150 plus 150, and that gets us our 450. And then finally, for the 600, 150 plus 150 plus 150 plus 150 gets us our 600. So obviously there's a pattern here, and this pattern seems to keep going on forever and ever and ever. So how does that help us get 100 months? Well, we now know a little bit more about how we're going to get there. We know that it's going to be 150 plus 150 plus 150 over and over and over and over again. The question that we really need to know is, well, how many 150s are there? And is there a faster way of adding those up? So let's see if there's a shorter way of writing these things. 150 plus 150 is just the same thing as 150 times 2. This one is just 150 times 3. This one's just 150 times 4. So we know for 100 it's going to be 150 times something, but what? Well, what's changing here and what's staying the same? Well, what's staying the same is it's 150 times something. What's changing is what that something is. So that has to depend on our independent variable, the number of months. So let's try to match those up. We have 150 times 2 when it was 2 months, 150 times 3 when it was 3 months, 150 times 4 when it was 4 months. So for 100 months, it should be 150 times 100. How does that help us get our rule? Well, we do the same thing for x. We know we're going to have a bunch of 150s added together, but how many? It seemed like the shorter way of writing it was 150 times the number of months, which in this case is x. So our f of x is just equal to 150x. That seemed like a really easy example, and you probably didn't have to do all of that work in order to find that rule. But the reason that I'm giving you that one is because it does get slightly harder. Let's look at another example. Let's just look at the table this time. We don't need to look at the graph. So let's look at x and g of x. We have our work. We'll go 1 is 13, g G of 2 is 19, G of 3 is 25, G of 4 is 31. Again, let's try to find G of 100. Why? Because that can help us find our rule. So when x goes up 1, G of x goes up 6 every single time. That's what makes it linear. We now know it's linear. It's a line because the growth is constant. Let's look at the work. So we start off with a 13, then we go 13 plus 6 to get our 19. Then we go 13 plus 6 again to get us our 25. And then 13 plus 6 plus 6 plus 6 gets us our 31. So we see a similar but slightly different pattern here, where we're starting with 13 and then we're adding a bunch of 6's together. So that's going to happen again for the 100. But again, the question is, how many 6's are there, and can we write this in a shorter way? So that first one up there, or rather the second one, is 13 plus 6 times 1. Then we have 13 plus 6 times 2, because there are 2 6's. 13 plus 6 times 3. This time, how many times do we have 6? Well, we have 1 when x was 2. We had 2 when x was 3. We had 3 when x was 4. So it seems like the number of 6's we have is 1 less than whatever x is. So when x is 100, we should have 99 6's. So that one will be 13 plus 6 times 99, which is 607. I don't care so much about the 607, but I do care about the work. I care about how we got it. So when we have x, and we're looking for a rule for g of x, we know we're going to have 13 plus a bunch of 6's. How many 6's? 1 less than x. How do we write that? X minus 1. So we have the rule g of x is equal to 13 plus 6 times x minus 1. That is the end. You can use this to find the rule for any linear function once you get it in a table.